So the paper that we are presenting is evaluating robustness of neural nets. As a summary, we will survey existing attacks. We'll go over the approach that they used in this paper, and we will more specifically go over 3 specific attacks that they developed. And we will also talk about how these attacks matched up, and we'll look at some metrics as to how effective they were. And finally, we'll briefly go over defensive distillation, which was the state of the art in defending against attacks, and see how it measures up. A quick summary of the terminology used in the paper. So in this presentation, we'll refer to the entire network as f of x, and then we'll refer to the network not including the final softmax layer as z of x, where softmax has this typical definition that we normally use. So they use various LP norms. Here, the notation used, x is the clean image, x prime sub I is the adversarial image that gets mapped to the incorrect class I, and delta I is the perturbation when added to x that makes it get mapped to class I. So the LP norms that are used in this paper are the L0 norm, which is simply the number of pixels changed, the L infinity norm, which is the max amount of change in a pixel, and the L2 norm, which is the square of the perturbation in each pixel summed up. Continuing on, so for the targeted attack metrics, there's a few different cases that we consider. One of them is the average case, which is the mean distance to adversarial images of each incorrect class. And so this is averaged over the incorrect classes. Best case is taking the smallest distance to an adversarial image of a averaged or over all the classes. So you're finding the minimum distance. And then worst case is finding the maximum distance.
Okay, so now we will survey the existing attacks that the paper has discussed. So the first one is box constraint LBFGS attack. The second one is fast gradient sign. The third one is Jacobian-based. And the lastly, we will discuss D-full attack. So firstly, in the box constraint LBFGS attack, as discussed in the class, so it's a white box attack, slow and targeted attack. The distance metric used is L2, and the optimization function is cross entropy loss plus the L2 distance metric. Then moving on, the second attack is white box. It's fast gradient sign. Again, it's a white box attack, fast and targeted attack. The distance metric used is L infinity. And in this, so we generate a new adversarial image by changing the gradient of the original gradient sign of the original image. So we simultaneously modify all the gradients at once. And then there is another attack. It's the progressive of this fast gradient sign. It's iterative gradient sign. So it's kind of a momentum based approach. And then we modify the gradient direction in smaller steps. Third is the Jacobian-based Saliency map attack, and this paper is basically derived from this attack. So this it's a white box, slow and targeted attack. It's a greedy algorithm, so we need to like run it multiple times so that it does not get stuck at suboptimal solution. So then we generate a Saliency map, and so there are two variants of this GSMA. It's GSMA F and GSMA Z. So as Zach discussed, so GSMA F is the feature vector just before the after the softmax layer, and GSMA Z is the feature vector just before the softmax layer. And then we generate a Saliency map like this. We take the partial derivative of feature vector with respect to the input vector, and we get a Jacobian, and we can see like which are the most significant pixels. So we transfer the original image pixel P to modify it to Q, considering those significant pixels, and Then the beta PQ parameter, we get like how much amount we need to modify the other pixels depending upon the alpha PQ. The last attack they discussed is default attack. It's a white box, fast and untargeted attack. The distance metric they use is L2. Optimization function is that it adds the perturbation until the original label of the image changes.
So in the new approach that's used in this paper, they start with the standard formulation, which is to minimize the size of the perturbation, and you want to minimize it, but under the constraint that the perturbed image is of a different class, and f of x plus delta is such that if it's less than or equal to 0, then it's of a different class, and also that x plus delta is in 0, 1, or rather that it's a valid image. And so they reformulate this, combining this constraint into the minimization process by using this Lagrange multiplier. So you have one minimization function and one constraint that it is a valid image. So here are 7 different objective functions that they propose. You'll notice that these are handcrafted to satisfy our original definition of our objective function, that f of x plus delta is less than or equal to 0 when it's satisfied. So here for this is loss is the cross entropy loss. So the if one of the non-true class probabilities are greater than or equal to 50% or 0.5, then this term right here will become 1 or greater than 1. So this entire term becomes negative. And if one of the other classes is greater than or equal to 50%, then we know that it's not going to pick the true class. So this follows our definition. Here in F2, it's simply saying the maximum of the untrue classes, so the maximum probability of the untrue classes minus the true class probability. And once again, once this gets large enough, then this whole thing becomes 0. This plus is just saying take the max between the value and 0. So it's like a rectified linear unit. Think of it like that. F3 is a similar definition. It's simply F2, but we've taken the soft plus of it. And you'll notice that when the argument here equals 0, we get log of 2. So we have to subtract it off. So once we've reached our objective, we want this expression to be satisfied again. Functions 4 and 5, I believe this should be, these both have errors in them. I believe this should be the max over the adversarial classes, because if we're minimizing this function, then we're maximizing this because there's a negative there, and we don't want that. The argument to this log is not defined, so I'm not entirely sure what this one is supposed to be. So you'll notice these first functions use the probabilities, and the second functions are, or the second set of functions, F6 and F7, are simply a restatement of F2 and F3, except we've instead sent in the logits to these functions. So we're using Z instead of F. And they found that F6 ended up being the best objective function.
Okay, so now we move on to the second parameter, that is x plus delta, that it should be between the range 0 to 1. So for this, they tried different approaches. The first one they tried is projected gradient descent. So in projected gradient descent, it iteratively clips all the coordinates. So the problem with this is that it alters the input very much, and such that the gradient descent, it performs very poorly in this case. Then the second approach they tried is clipped gradient descent. So instead of clipping the coordinates, they clip the objective function. So they do a maximization and then a minimization. The problem in this that while they maximize it, so sometimes the component gets such large that it goes out of bound, and when they take the partial derivative, it becomes 0. So the third constant that the third function they explored is the change of variable, and it's a tanh function. So we can see that xi plus delta I. So they just moved it over here, and it satisfies the constraint 0, comma 1, and it's ranging between 0 to 1. So it satisfies this constant as well as the function is smooth, so that the gradient doesn't become 0 when we take the derivative as well.
So here we've defined multiple parts of our problem. So we've specified different objective functions. We've specified different ways of dealing with box constraints, and we also have this Lagrange multiplier C. So in order to deal with that, to find the best combination, they simply brute forced all different combinations of box constraints and objection functions, and they minimize C using a binary search. And here will report the L2 norm of successful attacks and the probabilities of successful attacks. And this is on the MNIST data set. So each one of these blocks here gives the results for a specific type of dealing with the box constraints. And on each row we have the individual functions. So this mean gives the mean over the images of the size of the, in this case, the best case perturbation that led to a successful attack. And the probability says with what probability they were able to find one. So functions 2, 3, and 4 had turned out to be the worst. They scored the lowest. Sometimes they weren't able to find ones, they weren't able to find adversarial examples, and often, and always, their perturbation sizes were much larger. F6 once again had the best. It had the lowest mean perturbation, and it always had 100% success rate. Similarly, for the average case, and again, this is averaged over the classes for each image, and then mean is taken over all of the images. Once again, we see the same trend of these functions having lower success rate, higher perturbations, and F6 doing the best, and again, for worst case.
Okay, so now we move on to different attacks they proposed. So in this figure, you can see that they tried to modify the pixel of this class such that it can be classified as these target classes. And we can see that it's visually indistinguishable to um, uh, uh, check whether any pixel has been modified or not. So then this was the first attack, that's their L2 attack. So this is the objective function. It follows the original function that they proposed, delta P plus C into Fx plus delta. They put that box constraint 10HW. This approach is based on GSMA. So it's also greedy algorithm. And that's why they need to do multiple start so that they are not stuck at any bad local optim. The next attack is the L0 attack. So it's a non-differentiable metric and it's an iterative approach. They use L2 attack to eliminate the pixels. So in starting, they use the full image, and with the help of L2 attack, they found out the pixel which are unimportant, and then they remove those pixels. They focus only on the pixels that are important, and they modified it. And you can see in the worst case, they found out that when they tried to classify a 7 as a 6, so we can see that it's somewhat similar, look like 6. Then they made a note with the GSMA approach. So GSMA is just a vice versa of this. So instead of eliminating pixels, it include pixels. So that's why GSMA is less efficient because as it moves on in each iteration, the number of pixels grow with each. So the third attack is the L infinity attack. Again, it's not a fully differentiable function. Then they only penalizes the largest parameter, and the other has no effect. So that's why they get stuck in an oscillation. Then again, they propose an iterative attack with a constant tau. So It penalizes all the large terms and then it's repeated until convergence. And now moving on to evaluating their attacks. So firstly, they compared the L0 and L2 attack. And so they required 2 to 10 times lower distortion compared to previous attacks. And the success rate is also 100%. In case of L infinity, the perturbation they required is similar to previous one, but they have a higher success rate. And they also claim for the ImageNet with the Inception 3 model, V3 model, they can change any image to any label just by changing the last bit of each pixel. So previous attack, as we can see in the case of GSMA, as the model complexity increases, the effectiveness of that approach decreases. Whereas in this attack, as the model complexity increases with each iteration, the effectiveness also increases. Here we can see the result on ImageNet. So it's quite mean is quite large, but for the L0 attack, but it's only 0.1% of the image pixels, image size, because in ImageNet the data image size is around 299 cross 299. So, and GSMA fails to create an adversarial example from the ImageNet because in GSMA, as we saw, that it requires a pixel pair P and Q, and the image size is quite large. So each iteration we were unable to do it because the complexity was way too much. Then the second attack they is L2 attack. So they compared it with D full, and it's one third of like less perturbation they required. The third one is L infinity, and we can see that in the L infinity, in the average case, we get 10 times, we need 10 times lower perturbation compared to the previous attacks. So this was the case for ImageNet. So they tried Inception V3 model, and we get like 83% confidence score for dog. But when they add the attack, when they attack the image, so now the Inception V3 is classifying this image as a hummingbird with a 98% of accuracy.
Okay, so just a quick overview of how defensive distillation works. It was the state-of-the-art method to increase robustness, and it reduced attack success probability from 95% to 0.5%, at least for old attack methods. And it now has almost no effect on this new method. Once again, so this is the best case, so the smallest distance to a given class or to overall classes. The means here, I think, are slightly larger than before. And here we're reporting for CFAR as well. Before we were just doing MNIST. In the average case, we still have 100% probability, and in worst case, still 100% probability. So this means that they can not only find an adversarial image for any image, but also to any class.
Now, going through the strengths of the paper, so they achieved a 100% attack success rate for all the three metrics L0, L2, and L infinity, as well as they performed a 100% success rate on all the three datasets, MNIST, CFAR, and ImageNet. And simultaneously, they have a very small average perturbation compared to previous attacks, and they beat the robust network that the defensive distillation, which was state of the art, and it was able to like distinguish between the examples for previous attacks. The perturbed images, like it always looks like the original class, as we have seen that it was visually indistinguishable. Then they also did an experiment where they can just modify a few pixels of a whole black or a white image, and they can classify it into any class like 0, 1, or 2, and the image still looks like a junk. And the last is that they proposed a L0 attack in this paper, and it was the first targeted attack on ImageNet.
So as far as cons for this paper, we don't have too many. This was a pretty good one. So the biggest thing is that they presented these results, but they didn't perform any sort of speed test. So we don't have an idea or too good of an idea of how quickly it can be done. However, they do say that no attack takes longer than a few minutes on any instance. Another con that we noticed is that the L0 attack is actually dependent on the ability to evaluate an L2 attack due to the non-differentiability of L0 attacks. In quick summary, The paper introduces 3 new attacks on all the distance metrics. They also show that their attacks are more effective than previous attacks. The attacks proposed by this paper defeat the strongest defense, defensive distillation. The authors discussed about the various parameters that can affect the efficacy of an attack, and they propose high confidence adversarial examples for transferability tests and show that it breaks defensive distillation.